today we are going to talk about vectors in context or more of like applications. So we're going to look at a few word problems today, and we're going to talk about how we can use what we've learned so far with magnitude, direction, and component form, and how we can kind of put all these together and make some of these questions pretty simple to complete. So what I want to do is I'm going to start with number one. If you have graph paper, that's probably a good thing to use. It's not necessary. I'm not going to use it in this example, but it makes it easier for you to draw that out and to be more accurate with your drawings. But as you'll see, that's not really totally necessary. So we're going to start out, and it's talking about a person walking a certain direction. So we're going to say, I just need a starting point. So on your graph paper, pick a spot, and we're going to go 30 kilometers west. Right, so that's 30 this way. Then it says 20 kilometers north. I'm going to go up 20. And then it says going back 15 kilometers east. Okay, now these are all approximate directions. If you're on graph paper, you can get those exact. But what I want to talk about is that when it asks you for displacement, it's kind of asking you for a number of things. The vector that we are going to be discussing is the resultant vector, which is the vector you see in red. What I can do is I can create a component form for each of these vectors. Whenever you have a vector that goes just north, south, east, or west, writing the components is really easy. Right? For example, let's label this, let's be vector A, this one will be B, and the top one will be C. So if we said vector A, the components of A would be negative 30, 0, because I went left 30, and I didn't go up at all or down at all. So vector B, I went up 20, so that's going to be 0 in the x, but I went positive 20 in the y. Remember that up and to the right are positive directions, left and down are negative directions. Okay, and then C is going to be positive 15 and 0. If I wanted to know the resulting components of a vector, what I can do, and by far the easiest thing for us to work on, is simply to find the components of each of the individual vectors that you're kind of putting together and then add their components. Right? When we do this, we're going to end up with negative 15, 20. If you did a really good job drawing this vector, using maybe each grid as 10 kilometers, then you would go 1.5 kilometers to the left and 2 kilometers up, or 1.5 boxes and 2 boxes, right? And you can see that pretty obviously at this point. The question is what's your displacement? So magnitude and direction is what it's really asking for. So we can say, we can have A plus B plus C is really the vector we're looking at. We know that what we want to do is we want to find the magnitude of that, so it's really going to be easy. It's going to be the square root of 15 squared plus 20 squared, which is just 25, right? So that person is, distance-wise, it's 25 kilometers from the original spot. And then direction, theta, which is the angle measure. If we were to kind of think about this vector at the origin, it's going to be pointing just like this. So the actual angle measure looks like this. So theta is going to be tangent inverse of the two components, the y divided by the x, right? So 20 divided by negative 15. However, I'm going to have to add 180 once I finish that because my x coordinate is negative. If you do that incorrectly, you're going to get an angle that's negative in the fourth quadrant, but we're not in the fourth quadrant, right? So theta becomes 126.9 degrees. 126.9 degrees. I want to talk a little bit about that for a minute. That's what this is, this 126.9 degrees. Sometimes we have directions in different ways. And so I want to kind of discuss a few of the options of how I can talk about angle measures. Okay, one of them would be just simply to give you the actual angle. The other one uses north, south, east, and west. Okay, so if we were to find this angle, that happens to be 53.1 degrees. I just say 180 minus the 26.9 to get the 53.1. Now that's not 53.1. If I just told you 53.1, you think, well, that's in the first quadrant. So I have to actually characterize this by giving a bit of direction. So we would say 53.1 degrees north of west. That's one way, right? In other words, I'm going north of my cardinal direction west. The other side of that, I could give you the top angle, and I could subtract that from, I could say 126.9 minus 90. That's going to make this angle here 36.9 degrees. And so this direction would say 36.9 degrees. And now I'm coming from north, but which direction am I going? I'm going to go to the west side of north, right? So I'm west of north. You can see these two are related because I'm going opposite directions. I just have to give you that little tiny angle in there, right? So let's be really honest. That is the direction, just pure and simple, okay? But sometimes you get multiple choice questions and sometimes you get different varieties of answers. So these would also be possibilities, okay? But we get that the first angle, the one we found here, we said 180 minus the full angle, and I found this piece. To get this piece, I said this thing minus the 90 here, which left this piece, which is 36.9. Okay? For an FRQ, for like the questions you see here, I'm really not concerned that you give me one or the other. 126.9 is totally fine for this. Okay, the next question talks about when you have vectors or forces acting on an object. So let's suppose that two dogs are pulling on a bone that's stuck in the ground. Okay, one dog is pulling due west with 50 newtons of force. The other dog is pulling directly south with 30 newtons of force. What they want to know is what's the actual force being exerted on the bone itself if we combine these vectors. Remember that when we combine vectors geometrically, we add them tip to tail. So if I do it like this and I do the 30 on that side, right, instead of at the bone itself, then what I can figure out is this vector would be the actual vector that's being done on the bone, right? And so I'd like to know what that is. We know this one's 50, this one is 30, and this would be my new vector, the combination of them. Now, if I were to do this, technically it's asking for just the resultant force. So I've got a right triangle here, and yes, it's as simple as it looks. I could simply do the Pythagorean theorem and be done with it, right? So we'd say the square root of 50 squared plus 30 squared, and that would get me my 58.3 newtons. Now, sometimes I don't have just two vectors. Sometimes I have a lot of vectors. So in that case, I wouldn't be able to just use a triangle because there's not a triangle involved. But the way we would do this, the longer way, if you had multiple vectors, you would say, well, what are the components of my vectors? Well, the first one's negative 50, 0, right? I went to the left 50 and I didn't go up or down. The other vector would be, I didn't go x at all, I went straight down, so that's negative 30. So my combination, if I were to add these two vectors together, I would get negative 50, comma negative 30. And then I would do the Pythagorean theorem on the result. And if I had 12 vectors, I would simply just add all 12 of them together and get the resultant components, the x and the y, and then do whatever it is I needed to do at that point. Okay? The next one is one just like we were describing. What happens when you have a tremendous amount of vectors involved? How do I bring them all together? Okay, so off to the side of it, because it's so many, now I can get a piece of graph paper and draw this out. This is what happens when you get lost and you're just kind of making almost like a spiral. I'm going to actually just write down the vectors themselves without drawing it, just to kind of give you the other perspective. If we take it and we say, okay, the first one is 30 north, right? So that's going to be 0 in the x and 30 in the y. The next vector is 20 east. That's 20, positive 20 in x and 0 for y. 50 south, that's 0 for x and negative 50 for y. Remember, up and right is positive, left and down is negative. The next vector would be west 40, so negative 40, 0. And then 35 east, we have 0, nope, sorry. We have 35, positive 35 and 0 for x. Oh, I skipped one. Let's go back. We have, let's see, we got check, check, check. Get the 40, we need the 45. Okay, so 45 north, 0, and then 45 up. And then, so check, and then we have 35 east. So that would be the 35, comma 0. Double check, 30 north, we have 30 north here, we have 20 east, we have 50 south, we have 40 west, we have 45 north, and we have 35 east. Quite a few of these things. I would absolutely double check them before I just assumed I did it right, because I obviously skipped one myself. Now, because I have all of these, I can simply add them all together without having to really worry too much about all those combinations of vectors. I make sure I got the signs right, I make sure I put all of them together, and once I'm done with that, that's going to be what we do. So once we combine them all, we're going to end up with a vector of 15 and 25. Okay, so if I were to draw that picture out, you would have a lot of vectors put together, but to get to the end point from the very beginning, you would go 15 to the right and 25 north. And so when I'm giving directions, in this question here, it says I want my rescuers to go directly to the person. I don't want them to go around the world. If they're going to take a helicopter or whatever, they're going to want to go straight to it. So we need to give a direction and a magnitude for this vector. So 15, 25 is the vector. The magnitude of that vector is just going to be just like this, 15 squared plus 25 squared. This is going to tell us how far to travel. It's going to be approximately 29.15 kilometers. And the direction is going to be theta equals tangent inverse of the 25 over the 15. They're all positive, so I don't have to worry about any 180 involved. This will end up giving me something at 59.04 degrees, right? Obviously, there's a lot of ways I can describe that. That's this angle here. This is 59.04. I don't need to qualify that because that's in standard position, but if I did, it would be north of east. I could also give you the other side of that, the top down, if I needed to. You just say 90 minus that last angle, and that will get you the 30.96 degrees. And for the red one, it would be 30.96 east of north. Okay, so there's two different ways of looking at that one. The direct angle is perfectly fine here. Okay, next question. We're only going to do the first few of these. We're going to do A, B, and C. Now this one gets a little bit trickier. Here we have a river, and we have a boat on the river. We know that that boat is traveling across the river. Now the river, distance-wise, we know that this is 400 meters. We know the boat is traveling at 15 meters per second. We know the river is actually flowing this direction, south, at 7 meters per second. So the fact that the boat is traveling in the water, it's moving by its own propulsion, and the water is pushing the boat in another direction, they combine to give a new vector. So the boat, to someone who's standing on the riverbank, wouldn't just have a horizontal transaction. It wouldn't just transverse over the river in the same position. It would be moving down the river as well. So we want to figure out, for part A, what's the boat's velocity just inside the river. So we're really looking at a vector, this vector here. What is the magnitude of that vector, the speed of the boat inside the river? So here we go, river plus boat. We want to do that. We're going to do the Pythagorean theorem, or the magnitude formula. 15 squared plus 7 squared, and that is going to get me essentially 16.55 meters per second. The river is slightly increasing the boat's speed, because it's moving it down. So the horizontal component there is a little bit faster. The next part, so this is part A. Part B asks us, calculate the time it takes to cross the river. I have to be really careful about this one. The boat is going this direction across the river, and it's 400 meters. So how fast am I moving horizontally here? Well, originally we gave you the components of the boat's motion. The boat is moving 15 meters per second across, and it is moving 7 meters per second down. Right? If I'm measuring in a diagonal path, I'm going this fast, right? But I'm still only going across at 15 meters per second. So this is a bit of a trick question. I have 400 meters to travel. So we're looking at distance divided by velocity is going to equal time. That's the formula we're using. So 400 divided by 15 seconds, that's going to give me the amount of time that it takes to cross it, which is going to be 26.67. And how are you supposed to know that? Well, science. We've all taken science classes. We are in a pre-calculus course. There is a bit of expectations that you know how to do that. If you didn't know this little formula here, I would most definitely write it down. It's going to show up a number of times. And so distance, and of course you can solve that for all different things. Distance divided by time equals velocity, or velocity times time equals distance, right? All those things are essential. You're going to see that happen from time to time. Okay, and the last part here is part C. This one's asking, how far downstream will the boat be when it reaches the opposite shore? Well, now we're talking about moving down the stream, right? We're going to be moving down this way at 7 meters per second. So if I started here, I'm moving this way at 7 meters per second, and I'm going to do that for 26.67 seconds. So if I were to measure this 7 meters per second, and I'm going to be doing it for 26.67 seconds, then if I multiply those together, right, I'm looking to find the distance, right, equals the velocity times the amount of time spent traveling at that part. It's going to tell me how far I traveled. So we can go back. We're going to say we're moving at 7 meters per second times the 26.67 seconds that we're going to be in the river, and that's going to give you the final solution of 186.69 meters. Okay? And that's pretty much it. Okay? So lot here. Some of this stuff might be a little bit involved. My suggestion to you is go back over these questions. Try them on your own. You can even try number 3. It's a lot like the previous questions. But what I'm assigning for homework is just one question. I want you to try number 6. Number 6 is a lot like number 5. So take a few minutes. I'm going to post this worksheet on Canvas just below or just above this one, just above the video. Take a minute. The airplane question is a lot like the boat question. You're talking about, instead of a boat in water, you're talking about a plane in wind, adjusting that plane's speed. Take a minute, go back over these and try number 6, and we'll talk about them tomorrow.